you draw the line down to this x-axis, then the wet ball temperatures are marked. Those are the blue lines, the light blue lines that are running diagonally on this chart. So there's the light blue lines and also the dark lines. The humidity ratio is on your y-axis. And then finally, the relative humidity is those red swooping lines that you see on the chart. So from this chart, you can get a lot of information. And it has shown up on past tests. They were actually given a chart and asked to kind of do something similar to what we're going to do. So, the first point we're going to try and find is, I guess you can kind of put it out here. It's over here, so we're at -5 on the bottom and 100% red line is -10 when you drop it down. So it's actually a point. It's actually a point somewhere over here. Okay, so you see how we get that? -5 from here.
Yeah.
-10 is here, but we're at 100% relative humidity, so you have to draw a line over until those 2 points that intersect. So we're actually right there. So from that point, you can read off the values that you need.
I'm sorry, -10 should be X. No, I'm sorry.
Well, -10 is 100% red, so it's 100% relative humidity.
Yeah.
But then you have to drop that down onto the x-axis. So -10 makes actually a point, we're going to say, here. The second point is -10, it's actually right here.
Yeah.
So we want it at -5, so we'll just move towards on here into this area. So that's where we are. So from this point, we can read off all these other values. So the wet bulb temperature there, you're going to draw a line that's parallel to the light blue line, and read off the temperature that you're going to get, and it's going to be somewhere, say -6 is the temperature that you're going to get when you draw that line.
Sorry, I
Yeah.
still don't get the TS. Well, which one is the TS is the saturation?
The saturation temperature, so it's the temperature at 100% relative humidity.
Oh, okay.
What you're going to see is when you're on that line, whenever you hit -10, you're at that point, on that very top red line. So this is 100% relative humidity,
Yeah.
and you're on that line, then you have -10 right here. So then you have to draw a horizontal line across so you intersect the -5 that you are on the dry bulb temperature. That's how you end up at that point. You'll see as we keep going through, that's how you can see where these points are.
Sorry, and the light blue is -6 because it intersects.
Yeah, because you're going to draw another. So basically now, from that point, if you have the chart, you would draw, like, say, a dot, and then you're going to draw a line that's parallel to that other light blue line.
Oh, and it hits the...
So it hits, so it hits the 100% of humidity, then you're going to draw a line down, and whatever temperature you read from the bottom axis is going to be the temperature, so that's how you get -6. Okay, so then your humidity ratio is the y-axis, so then you just you continue your horizontal line all the way over here, and read the number off, and these are just estimates. I mean, it's not, you might estimate something different than is in the solutions or that I did when I did it. Okay, and then so then we go back over here to our point, which is somewhere over here, and now we're at the relative humidity. So when you actually put a dot where this is, you it should be somewhere in the neighborhood of 0.7, so it's around 70%.
Yeah.
That's red from those red lines that are swooping up and down there. Okay? So then we can go to the next point, which is 5. So we're plus 5. And our light blue line is 0. So we're actually right about here on the chart. So from here, now we're looking for the saturation temperature. So 100% red. Is the temperature that you're going to read from going this way until you hit, whoops, I mean zoom in. Actually. So that's the temperature that you're going to read when you go horizontally this way until you hit 100% on the red. Why does that like change the zooming and everything?
So the 5 would be.
Okay, so you're somewhere over here when you get there. I have minus, and once again, this is an estimation. I have minus 9 on the solution, you'll probably see minus 12, so let's do minus 10. And so let me go back to our point 50, and we're relative the humidity ratio, which is on the y-axis.
Sorry. For TS, it go horizontally to the left and until you hit the 100%.
Yeah.
But I don't see it can hit actually. It's like it's never hit the 100% something.
It probably does drop. Yeah, it does if you actually drop a point.
Okay.
If you get a rule around and drop, it'll actually hit 100, and then you take the temperature that you read off the bottom, the x-axis. So then your relative humidity estimated at, or your humidity ratio, sorry, that, and the relative humidity in the red line, somewhere in there. Okay, so third point, we're at 15, which is here, and we have a humidity ratio. Right. So our points are over there. So once again, we do the same thing. We're reading out the chart. This time, our horizontal line that we draw is actually on there. So you can see it goes all the way across 100% on the red line. You drop the line down, you get about 4, right? Okay, then our saturation temperature, you're drawing the line parallel to the light blue line. So then where the line intersects, drop the line down, you get about, it's obviously less than 10, so 9. And the final one, the humidity, relative humidity, that you just estimated between your red line and...
Which is the relative humidity? The red line, right?
Yeah, the red line.
For the 30 years.
40.
40 feet or so. You're between the 40 and the 50.
Oh yeah, it was
40.
It's kind of, I don't know what happened, kind of right, but yeah, you're between the 40 and the 50. I mean, these are just estimation. I mean, when you look at it and measure it, as long as you're within, you know, like a relative roads of error, or these kind of numbers, or within a ballpark, you're doing right. So then we go 25 on the bottom, 0.6 relative humidity, 50, or our points right over here. Do the same thing again. Our horizontal line is the draw. You're going to come out. You're going to come out in between 15 and 20 somewhere. Call 17. Your parallel line, obviously less than 20, but you're pretty close to 20, call it 18. The humidity ratio is your horizontal line coming back to this y-axis here. So you're obviously greater than 10, less than
0.012.
yeah. Yeah. Okay, so the last point, just more trick than anything. Not even sure. Same thing, you're at 30 and 1, so you're all the way up here.
5.
So this time when you draw your horizontal line, you're already right at 20. So the saturation temperature is 30. When you're at 100% relative humidity and a dry bulb temperature of 30, the saturation point is 30 because you're at 100% relative humidity.
Excuse me. For the second row, the humidity ratio,
Yeah.
I think it would be around 0.002 something. It's point zero, like it's like 0.002 something, right?
I have the same thing over here. That middle one?
The humidity ratio, yeah.
When you're at 0,
No, it's about 0.05. So.
yeah, as long as you're within that ballpark.
Oh no, it's the 0.015 is bigger.
Yeah, it's just 0.015. It should like at least 0.0015 something.
Really, I think it's between 0.005 and 0.01 because it's 5.
Yeah, I have actually one on the answer they say.
It's 5.
Yeah, I have an extra 0.
I think it's the lowest part.
Yeah,
like,
I have an extra
lowest
0.
bracket. Like it's
So you're saying it should kind of be like this. Something like that?
yeah.
Yeah, that's what I have on my answers. This answer is within a 0. I can mark that down and change that to a solution. Okay, good call. Good catch on that one. Let me know. Okay, yeah, this one looks like. Okay, so then the wet bulb temperature, it's also 30 because the line that you're drawing parallel to the blue line is actually right there at 30. And the humidity ratio, you're drawing the horizontal line over the y-axis here, and you get you're greater than 25, so seems better. Okay, so that's a pretty basic way of how you can use this chart. Just giving 2 points, find out all this other information. Not too hard, pretty easy to figure out. I really wish this came.
1.
Okay, so you all have this copy now. To the next question that we're going to go on to, I'm not really going to, it's more of a hand moving exercise, but it involves the shirt. Question number 4. Okay, it says assume you have a perfectly insulated room with a measured temperature of 25 degrees Celsius. So then question A, say, what is the initial humidity ratio of the air that can produce the lowest temperature through evaporative cooling? What is the final temperature and final humidity ratio? So, when the question we're given, we're at 25. So you pull 25 off the bottom, which I've marked there for you. And we're looking through evaporative cooling.
So you make it to 100% humidity because it's maximum saturation point.
That's for the final, yeah. Yeah, that's exactly what I've drawn on there. So as you're evaporative cooling, you're adding, like, say, mist to a room and it's cooling down the room, which means you're traveling along that, say, like along one of the wet bulb saturation temperature, light blue lines, until basically you hit 100% relative humidity. That's going to be your final, because at that point you can't saturate the room anymore to cool it down. I mean, at that point you're so saturated that you're at 100%. That's the coolest that it's ever going to be. So from that point you can drop a line down and what I estimated around 9, and you can pull the relative, the humidity ratio off the same point. So it's not really a calculation or anything, it's just more of drawing lines on the chart and seeing where they end up. And then part B, what is the initial humidity ratio of the air that can produce the highest temperature through condensation warming, and what is the new final temperature and relative humidity ratio? So now we're looking at warming the room up. So essentially we're starting out at 100%. We're starting out with the room being completely saturated, and we want to warm the room up. What is basically the final temperature that you can end up with. So once again, going to the chart, you're 25 and 100% relative humidity. You draw a point there, and once again, you're going to travel along that saturation temperature line again. So those light blue lines are going to travel down at this time though. So when it's asking basically what is your final temperature going to be, and basically your final temperature is going to be when there's no more moisture in the room, basically, like you basically evaporated all the water, so your humidity ratio is 0 because there's no more water left in the room. And you pull the temperature off, which you kind of have to extrapolate basically to get to that point. But if you just took the slope of that line and drew it down, or even if you draw it down, kind of roughly estimate, you should be around 75 in that ballpark. So there's no like direct calculations for any of this. It's just more of a plotting point and drawing lines on this chart. So that's not too hard either.
Sorry, TW is temperature water rate.
The what?
TW?
The TW is from the first part?
Yeah, sorry.
Yeah, the wet bulb temperature.
What?
The wet bulb temperature, so it's those blue lines.
Those wet bulb temperatures. I'm not sure what wet bulb is.
You don't have humidity,
Oh.
right?
Go ahead.
It's wet bulb is you don't have humidity, right? Like,
Well, wet bulb would be like the wet, like...
oh, the wet bulb is
like if you have moisture, basically, you're going to be on
yeah.
somewhere.
Sorry.
where that bottom line is completely dry. Okay, so number 4 is in the calculation, and that's just like I said, a hand waving exercise for me in drawing lines that you would draw them. Okay, so did everybody copy that down so you can go home and kind of think about it? And, that was the question that was on last night. That's the only type of question. Only they were different. Saving is only 5 minutes. Yes?
So in what you were assuming that the air is saturated, like completely saturated at 25 degrees.
Yeah, because it says it's for condensation warming, so you're assuming that it's completely saturated at the beginning, and you're warming it to basically where there is no more moisture in the air. Which is that's why you end up back down on the x-axis with the 0 humidity ratio. So we're going to move on to question number 5, which is just a quick calculation, but it kind of throws you off because the units aren't what you're used to. Okay, we don't need this chart anymore. Okay, so question number 5 tells you basically have a 50-meter tall experimental test system that is designed to capture energy per square meter. Designed basically to catch 25 megajoules per meter squared. So we have a 50-meter tower that's designed to capture that much energy. And then the question's asking you, what is the estimated temperature rise of the test rig if it contains only dry air? So like, kind of visualizing it, it's obviously not, well, say we have a box. Okay. 50 meters tall, that's all we're really tall. Doesn't. And designed to capture 25 megajoules per meter squared. Okay, so all of our atoms are designed to capture that. So we're asked to estimate the rig temperature if it's only got dry air, say, on the inside. So on the inside, it's only got dry air here. Okay. So this goes back to stuff that we did kind of in, I think, probably the second week. We're going to look at questions. So this is A, the temperature of just dry air. We're going to look at equation, so that the change in energy is mass, some constant, until C. So what throws you off in this question is that you're given C, for dry air, as being joules per meter cubed. Okay? And it's the units that kind of throw you off, because you're typically used to seeing this K constant. You can kind of just figure it out from looking at the equation what it should be, because this is a mass. So you're used to seeing it in, say, joules per kilogram Kelvin.
Okay.
Actually, this is another error in this thing too. This should two areas of problem set. Okay? So you're kind of like, how am I supposed to get rid of this M?
So the density of air and define pressure.
Well, you could, but you don't know what
the
the pressure is, you don't know what the temperature is. I mean, you're asking to calculate the temperature, right? So you don't know enough to be able to see this M, but it's because of these units that's throwing you off. So other terms, I've just kind of done this problem as if I haven't even done it. That's kind of what I'm going to do today. So my first thing is if I see this on a test, so this is going to be helpful for you, is throw the numbers in there that you know. What are you going to end up with? What units are you going to end up with? Does it look right? Does it look wrong? So let's just throw numbers in there and see what kind of units we end up with. So we have the change in energy of this, 25. This is why it's key to write down your units. And I'm going to do times 10 to the 6. So I get joules per squared. And I have this M. I really don't know whether I'm going to end up needing it or not needing it, because I have no way of even knowing how to estimate it. Times 1200 joules per meter cubed Kelvin times our delta T. So I'm looking at it on my test, I don't know what I'm doing, I'm a clue, I'm going to sit here and be like, okay, well, yeah, exactly, cancel some things out, I can divide these numbers, so I'm going to end up with something that's going to be delta T is equal to, if I divide the numbers, and it's M from that M, but its units are actually going to be meter Kelvin. Okay, so I saw this goofy M again. I have no way of estimating it, but I know I'm looking for a temperature change overall. So, hey, look at, I kind of have, I have a distance here, say a length, I have 50 meters here. I can divide this, get rid of that, divide it, and I'll end up with Kelvin. So if I do that, I have delta T. So I'm just going to divide this by 50 meters. And I get delta T is equal to 417 Kelvin. And when I see 417 Kelvin, that's when I'm like, oh no, that doesn't make any sense. But then you kind of got to sit back and look at what we're doing. So even when you read the solution, it doesn't go through like this process, but you end up with the answer is actually 417 Kelvin. You know, this is huge and it's really unrealistic. And the main reason why it's huge is because you don't have any evaporative cooling going on. You're just looking at dry air completely, which in real life never really happens unless we make it happen. And you don't have any of this vertical transportation of heat through this. Like we're just looking at it as just all heat basically, and everything that goes into it is that.
And we assume that the dry air has to be at least 417 minus 273 Kelvin, right?
Well, to produce substance.
Because it drops, the temperature drops, right? From condensation.
Well, yeah, that's what we have to get condensation in it. But we're just looking at dry air right now.
Yeah, so I mean, like, when you absorb the water, right? The temperature in the air cools, right?
Yeah, that is the next question.
Divided by the height?
Yeah.
The mass? How does the mass get?
The mass, because of this fact here, which is key in this question, because this is what C is typically given as, right? Because you have this mass here, but we were given a C of this with no mass. So looking back at it, you can actually cancel out before you even start because you know it's already been taken care of in this equation, or when you're given that Z. Okay? So that's A, and then B, what is the change in temperature if the bridge contains a 2 centimeter thick layer of water in its base, and the air and the water are at the same final temperature, and no evaporation occurs. So this is also, once again, another unrealistic case, because if it's heating up, you're going to get evaporation of the water. But we're going to assume for this case that there is no evaporation. So let's go through and calculate this one and see what the change in temperature is in this one. So heat. Okay, and this goes back to, I think, the first or second problem set. The key thing in this one is remembering that 1 kilogram of water covers 1 meter squared in height of 1 millimeter. Okay, remember that's in like the second problem set I think we did, or the first one even. Now this comes from your density of water. Okay, that's where that comes from, right? So if you have 1 square meter of it, so if you divide 1 by 1,000, you're going to end up with 1 millimeter, kind of basically what your volume would be. So using that fact, we can determine the weight of water of 2 centimeters. So therefore, 2 centimeters is equal to 20 kilograms H2O per meter squared. Then you have to know the specific heat of water, which I think we also talked about in the same problem set that was, but I'll give it to you again. Specific heat of water is joules per kilogram Kelvin. So, since the question told us that they both end up at the same final temperature, we have to kind of make a combined specific heat equation that combines both the water and the air together to give us like a combined specific heat for the two same mediums. So combine specific heat. And to do this, you got to use from part 1, you have to use the C. So you have 50 meters, which is the height of our grid, times 1200 joules per meter squared Kelvin, which is the C from right there, plus 20 kilograms of water times the specific heat of water. Right here. So, basic thing when you're writing numbers, Have those.
Don't you want to multiply the 20? Oh yeah.
Yeah. So basically, when you're adding numbers, just make sure you're adding the same units. Kind of cancel that out. You get the meters squared. So you're adding joules per meter squared Kelvin to joules per meter squared Kelvin. So you're adding the same thing together.
So it doesn't matter the 2 centimeter of water in the 50-meter tank.
Yeah,
this is
we're taking care of that right here. Remember?
okay.
This 2 centimeters in water is actually.
Yeah, but actually the air's got a the height of the air got smaller.
Yeah.
It's like a 2 centimeters.
Yeah.
It doesn't matter.
Really precise, yeah, it's changed, but it's not going to make any difference in your significant figures. Okay. I'm going to just come up here and do it. And this gives a delta T of joules per meter squared, and then divided by. So you get 174 Kelvin with a little bit of evaporation. Or no evaporation, but at least there being water in there. Yes.
The reason why we are taking the combined specific heat is because we are reaching the same final temperature for
Yeah.
So if it's not, we're not. So we're gonna do separately.
Yeah, you have to calculate it separately. It's a lot more complicated calculation than just a simple addition.
This is 174 drop, right? This is the equation. 174 Kelvin drop in temperature.
From the first one?
So no, I mean part B.
No.
Right?
No, it's still you still climb the temperature.
Line.
Yeah.
I thought you evaporated.
We didn't evaporate anything. So it's asking for the temperature. The temperature change, yeah, so it's no problem. Yeah. You didn't evaporate anything. And even if you do evaporate something, it's still not enough to make it cool.
Okay.
Because that's the part C is how much more part C is finally what is the resulting temperature rise of the water and air both reach the same temperature at 5 millimeters. 5 millimeters of water is allowed to evaporate. The only way to get that cooling effect is if you're almost like misting it in, right? You've been to like Canada's Wonderland, places like that. I think I've lost one of those in Canada's Wonderland. They have that Coke cooling station or something, and you walk through it, they're misting it into the air. You get that fine particle. Just evaporating water doesn't necessarily mean it's going to cool.
Actually, went last weekend.
Canada's Wonderland?
Yeah.
To the Halloween night? We were supposed to go see it, but we didn't have time. Any good?
Yeah. It's kind of busy though.
Yeah.
Yeah.
Okay, so let's do C elements. And it's just pretty straightforward. Going back to the same problem set where we talked about all these things. So the first thing that you're going to do is amount. You got to determine the amount of energy used to evaporate the water. So this comes from the rate of evaporation. Q is equal to M. What is the graph? LE.
The water is 5 millimeters.
Yeah, so we have, so then we got to remember from part B where we did 2 centimeters, so 5 millimeters of water is actually equal to 5 kilograms H2O per meter squared. Yeah, it's 5. And then LE, remember from before when we talked about it, it's 2.5 megajoules per kilogram. So you can figure out Q now being 5 kilograms squared times 2.5 megajoules per kilogram. So we need 12.5 megajoules per meter squared just to evaporate 5 milliliters of water.
Meter squared. Sorry. 2.5 times 10 power 6 kgK.
Where?
Sorry, is that right for you guys?
Here?
For kilograms, is that right?
Yeah.
Okay, sure.
And then, so it takes, so we have 25. So then you got to determine how much energy you have left for the actual temperature to rise. So, just trying to write this down. Energy for temperature rise is, you have 25 coming in. You're using 12.5 of it to evaporate. Please use 12.5 megajoules per meter squared per temperature rise. Okay, and then since they're both going to the same temperature, we have to do that combined specific heat again. So you can just determine delta T from that just as last time, which you have that calculated. That's 12.5 times 10 to the 6 joules per meter squared over what we calculated in part B for the combined joules per meter squared Kelvin and 87 Kelvin. So then there's part C, but it's just explaining what's going on. You can read that. And the last one we're going to do is question 6, which is using.
It says some the amount of energy to evaporate water. So you did 25, that's 12.5. On that here, energy for temperature rise, right?
Yeah.
Why did you take 25?
That's because that's what we have coming in. Remember the question is us?
Oh, yeah.
That we have 25 megajoules per meter squared. That's what the rig is designed for. So that question's a little bit tricky. It's math's not hard, but the main thing is it's more following units. That's why it's always key to write your units down. I usually don't. But key you should be doing. especially on these questions, because as you've seen in the test, you'll get answers that are 1, 10, 100, 0.1, and they're all off by factor of 10, and if you happen to say, followed your megajoules and maybe turned it into, say, and you divided it by joules, but didn't take care of your megajoules, that's when you end up in this problem. So that's why it's key to write down your units. So, question number 6. Using the perfect gas law, the hydrostatic relationship for connection between pressure and density in the atmosphere, and assume an unknown lapse rate, describe temperature decreasing with height, which is what lapse rate is, derive the relationship between pressure and temperature. So this question is asking you to derive a relationship between pressures and temperatures you go from one place to another place. Like, so you have P1 and P2 and T1 and T2. So you have pressure and temperature in one place, you have pressure and temperature in the other place, and it's asking you to find a relationship between the two. Using these 3 things. So let me just put this up. So let's write down these laws that we're going to start with. So we have the perfect gas law, and we're going to use P is equal to, two P's like that, so I'll probably get 18. It does get these will start to look like this. I'm going to put a little tail, I guess, on the pressures. So we're going to call that equation 1. We have hydrostatic pressure. And changing pressure. We're changing distance. Is equal to minus. I'm putting these A in there. These are like for dry air, so we're kind of, or for air actually, it's A. We call that equation 2. And we have an air lapse rate, which is changing temperature, or changing height, is equal to minus the lapse rate. So we're going to call equation 3. So those are the 3 equations that we're told to use to derive this relationship. So I'm just going to write these down and try and make it fun. So from equation 1, you can get your density is equal to pressure, gas constant, T. So then you can sub TA into 2 to get dT by dz is equal to minus T G R A T. which you can rearrange to get dt by e equal to minus g r a t d z, which we're going to call equation 4. Okay, let's throw this one up and down. So we're a third of the way there. So now we can rearrange equation 3 for dz. From 3, you can get dz is equal to minus dt over alpha. Then sub dz into equation 4. We're going to get dp over p is equal to minus g r a t times minus dt over alpha. So I'm not going to rewrite that, but obviously a minus times a minus will cancel out. Actually, here, I'll rewrite it. I ended up with it in the form. So you can rearrange that and minus. You end up with dp is equal to g over r a alpha dt over t. Now I can do everybody's favorite thing. We got to integrate that. Sorry. Because once again, we're trying to figure out pressure and temperature at 1 and related to the pressure and temperature at 2. So you got to integrate. So we need to do the integral from T1 to equal to G So G over RA alpha is a constant. You can move that to the side. So then we have this.
Log
Yep. So the integral of dp over p is ln t. Then on this side, so you're going to get ln t2 to t1. evaluate one minus 1, 2,
Wait, is it 1 minus 2 or 2 minus 1?
Doesn't matter. Oh, it's 1 minus 2. 2 minus 1
Sorry,
actually.
yeah.
2 minus 1. But as long as left and right are consistent, like you can
Got the other
switch
side,
the same. Yeah.
So that's what you get, and that can be simplified. I'm not going to simplify. So go back over here.
Wait, how do you get rid of log on the side? On the right hand side, how do you get rid of log?
What's the same thing? Oh, sorry.
It's long each.
Same thing, yeah. Okay, right down there. I was more worried about brackets, so remember to multiply. There. Okay, so you can simplify the answer for essentially, but you can simplify it. Ln minus ln is actually going to be 1. Make sure I write this down right. Which then you can simplify one more step. You can move that up and make it an exponent. Take log of the thing. And I'll write the final answer. You got a log of both sides. 2 equals 1. 1 That's the end. And questions now. Yep. Don't worry, I've never seen
Yeah,
it.
it's 2 key one, by the way.
Ah, man. The end of the day. Yeah, make sure you got my name. And don't worry if you've never seen integration. I can't remember that. I've actually never seen a show like that. So I've seen like the final equation that you might need to know, but you've never had to derive it. But that doesn't mean you might not have to.